In problem set 10, we begin to see some of the effects of non-ideal solutions. And we'll have a number of problems where we can examine this. It starts with problem 1, where we're given a mixture of ethanol and water, and we're given data for their mole fraction and then the partial pressures of both ethanol and water as a function of that mole fraction. So the mole fraction increases for ethanol as we move down here. And what we want to do is derive from this information the Henry's law constant. Now, I'll remind you that if we were to draw a vapor pressure diagram for a binary mixture that went from, let's say, 0 to 1 in one of those components, I'll say component A, the vapor pressure of A would be basically 0, well, would be 0 at 0, but it would be something non-zero for component B, and then it would increase up to whatever the vapor pressure for A would be at a total of 1. So this would be a Raoult's law diagram. All right, when we don't have an ideal solution, however, we can get things that jump up a little bit like this, and then as we get closer to the end, we sort of gradually approach that. So we have two different types of behavior here. We have one type of behavior here where the slope is like that, and another type of behavior at the other end where the slope looks more and more like the Raoult's law slope. So this slope over here is what is Henry's law. And this slope over here that approaches the Raoult's law slope is the Raoult's law. So what we're looking at is a picture of this pressure of ethanol, and here we've taken away the pressure of water, so we're going to eliminate this from the consideration. So this is a sum of the two. What we have here is really more a diagram of just looking at what is the pressure of the ethanol part. So as a Raoult's law thing, it would go up like a line, and when it is non-ideal, then it might go something like that. All right, so you need to use this data to somehow get a handle on how big the change is at this end. Now, I recommend a numerical method. In fact, that's what the problem basically suggests that you do. I will tell you that one possibility is within Wolfram alpha, there is a function you can use called cubic fit. And cubic fit, you can also have quartic fit, or I suppose fifth order fit and all of that. You have different data points that you provide it inside of these sort of curly brackets. And you can give any number of these points. I will say that for a cubic fit you probably need at least 3 or 4 points, but you can give it 5 or 6. And then it will give you back an equation that will fit those points to a polynomial of order 3, cubic. So, you know, the highest value will be an x cubed value, then there will be a term that is an x squared and a term in x and so forth. So then you could use that numerical fit to the data, appropriate data along this group of data, to actually find something that would tell you what the Henry's law constant might be for that. Okay, recall that the Henry's law constant is going to be some constant times the mole fraction of that value as the mole fraction approaches 0. All right, that's the official definition. All right, so a little bit of work to get this one, but I think it's good work that helps you become acquainted with numerical methods as a way of solving for some of these problems. All right, in problem 2, we're going to have a liquid mixture of chloroform and acetone that have a particular mole fraction of the acetone. Okay, acetone is B, so B equals acetone. And we're given the mole fraction in the solution. And we know that the pure vapor pressures of these things as a function of temperature, so this is giving us pure vapor pressure of chloroform as a function of temperature, pure vapor pressure of acetone as a function of temperature, are these two expressions here. So for whatever temperature we happen to be at, and in this case it's 300 K, we can calculate what the pure vapor pressure is for each of those substances, and then we could use the mole fraction, if this is an ideal solution, to find what the vapor pressure is for the solution. And that's essentially what you're going to do in part A. Okay, we're going to treat this as an ideal gas. So when you're done finding the vapor pressure of this solution, then you'll need to convert to find the mole fractions in the vapor phase. Okay, and this is what we're going to assume an ideal gas. So remember, for an ideal gas, Dalton's law is the operable way to convert from partial pressures to mole fractions. All right, in the second part now, we're going to venture into the realm of non-ideal solution. All right, and what is the game plan here? Well, if we had an ideal solution, remember that the vapor pressure for whatever component is going to be just the mole fraction of that component in the solution times the vapor pressure of the pure stuff. All right, when we don't have an ideal solution, we want something that looks like this as much as possible. So instead of having mole fraction here, we use the activity of that substance under these conditions. So in other words, the vapor pressure of this would be the activity times this pure vapor pressure. Now this quantity is going to be the same whether we've got an ideal solution or not, because this refers to the pure substance A. All right, so this is going to give you a way to get to the activity if we know, for example, the pressure of a substance and its pressure as a pure substance. All right, now we're given a mole fraction of component B in the vapor phase. We're given Y sub B. Well, from this, you should be able to get Y sub A. All right, that is a fairly straightforward thing. So we should be able to use this, the information given in this problem, because we have a mole fraction, we have a total vapor pressure for this solution, and we have vapor pressures for these components as pure substances. We should be able to get the activity, and we also should be able to get its activity coefficient, because that is going to be related like this. All right, so use this information with the information that's given here and the relationships between mole fractions in the vapor phase and mole fractions in the solution phase. You should be able to get a handle on these things. There are no difficult calculations here, no integrals to perform. Just it's a matter of working out what it is you need to use in your calculations. Okay, in problem 3, now we're going to have a non-volatile organic solute. Okay, so we have now moved out of the lessons that dealt with volatile solutes, and we're with non-volatile solutes. And it's in 100 grams of benzene. And this mixture boils here. So this is the vaporization temperature for the solution. This is the vaporization temperature for pure benzene. All right, so there is a change from one of these to the other. And we have the heat of vaporization for benzene is essentially 30.77 kilojoules per mole. So now we're asked, what is the boiling point elevation constant? Well, we've got all the information we need here to get that. And this is a shameless plug, but you should take a look at the video tutorial, Colligative Properties of Dilute Solutions, because it will eventually tell you why this has something to do with this problem. All right, so you'll use all of this to determine the boiling point elevation constant. I'll note that this is also very similar to one of the basic skills problems. So the main challenge I think you'll have here is you need to make sure you get your units correct. You need to use the correct units so that the right ones factor out, and you have a target here. These are the units that you should have for the constant that you evaluate. Now, the second part of this problem is we need to know the molar mass of this unknown solute. Well, how are we going to get that? Well, generally speaking, what one finds is that the change in for example, a vaporization temperature is going to be the boiling point elevation constant times a molality of the solution. All right, so what we're going to need to do is somehow take this number of grams and relate it to the molality that we get if this is the change in temperature. Well, we're given two temperatures, so we can figure out what the change of temperature is for that boiling point. We have just gotten a boiling point elevation constant from part A. Now you just got to figure out how to find the molality of your solute, and then use that information with the information given in part A, especially the grams of the solute that you have, to determine what the molecular weight of the solute is. Okay, it's a fairly straightforward determination of molecular mass, and this is actually exactly how you would do it in real life if you were making these measurements. All right, another colligative property is osmotic pressure, and I'll just remind you that the equation for osmotic pressure is the concentration of the solution times RT is equal to the osmotic pressure. So this is a pressure that is going to have units of pressure. So those could be bars, could be atmospheres, could be torr. All right, but whatever unit you end up with here has to come from these things that are over here. All right, so this is another problem where you need to be very careful to pay attention to the units and make sure you're using the right units as you go through. Now, the first part is just a straightforward exercise to find the expected osmotic pressure, and you're given the units of pressure that you should target for this, so that will tell you something about how you want to position these various quantities that are present here. You're given a certain number of grams of a protein that produced that. Whether that plays into this or not is for you to decide. You might want to pay attention to the molecular mass that's given for this protein. All right, so find pi for part A. For part B, we're going to use a different protein, and we're given the amount of grams that are dissolved, and we're given the the water that is used to dissolve it and the temperature, and we're told what the osmotic pressure is. Notice that the units now are torr, are the pressure units. Okay, but we're also given that same thing in bar. Okay, so you can use whichever one you want. All right, but when you use your formula for osmotic pressure, make sure that your units are going to work out for this. Now here, just as in the previous problem, problem 3, we're going to find the molar mass of our unknown solute. Okay, so once again, you will use the formula that you have for osmotic pressure to determine something about the number of moles of this unknown that you have, and then combine that with the number of grams to determine a molecular weight. All right, in the last problem of the problem set, we're now going to deal with an electrolyte solution. So lesson 5E will come in handy here. All right, and we're going to assume that we have an aqueous solution of sodium chloride with this concentration in molarity, moles per liter. And what we want to know is what is the value of its ionic strength, and there is a basic skills problem related to this, so this comes straight from that. And what we want to know is what is the ionic strength of the sodium chloride, and then we want to find out what is the concentration we would need to have of a magnesium chloride that has the same ionic strength. So we want a magnesium chloride solution with the same value for the ionic strength. All right, this isn't a very difficult problem, but you will need to pay attention to the kinds of ions that are present in these solutions and what they mean for this formula here for the ionic strength. All right, now we're going to use those formulas and the Debye-Huckel limiting law, which is written down out here, to find the mean activity coefficient for this particular system, for the sodium chloride Well, actually, we're going to do it for both sodium chloride and for the magnesium chloride. Okay, so you're going to have two of these to calculate. All right, we're again using this situation where they have the same ionic strength. In fact, we're using this solution up here is what is used to calculate the mean activity coefficients for sodium chloride and magnesium chloride down here. All right, again, this should be a fairly straightforward exercise, but you will need to know how to generate the numbers that go into this theory so that you can get the right answer. Now, I would recommend using the simplified version of the Debye-Huckel limiting law, but if you want to use this more complicated version, power to you. Good luck with the problem, and please let me know if there are any questions.